All right, so it's a pleasure for me to be here in Troyes for the second year in a row. Last year, it was not possible to do the lecture on site. It had to be online, so I'm happy to see the faces of the students this time. So my name is Javier Cerrillo. I come from Universidad Politécnica de Cartagena in Spain. And before we start with the lecture, let me explain a bit where I come from and what is the reason that I'm lecturing today. So you probably, well, I don't know how aware you are of the city of Cartagena. It's a small town by the sea in Spain. It's exactly at that point there. And it used to be a very important town. It used to be the capital city of a Roman province, Cartaginensis. And back then, its name was Cartago Nova. So it was founded by the Carthaginians from North Africa. And we have a lot of Roman remnants, Roman heritage there, and also from other cultures, Punic cultures as well. And this is how it used to look like back then. So a nice port with all the things that a Roman city needs, right? And nowadays, Cartagena is part of this large alliance of 8 universities. The European University of Technology, you have probably heard of it, and you have seen some posters outside on the corridors. So it's 8 universities. UPCT, Universidad Politécnica de Cartagena, is one is part of this alliance. And as you can see, we have a nice campus by the sea. So you're very welcome to visit. This is how the city looks nowadays. We have nice views on the port, the sea. We have a nice regional park with beaches that are completely untouched. So it's a nice environment, and if you're interested in doing a bachelor thesis, just get in touch with me or some of our colleagues. There are some exchange opportunities through this European University of Technology, so get in touch. I am the leader of the group of quantum technologies in my university. This is how you can get in touch with me. This is some collaborations that we have ongoing with my previous employers. And the topics that we work on are quantum communications, so how to fully, safely transfer information between partners. Quantum computation, which you're learning a bit about in this lecture. So how to exponentially enhance computational power, and also how to use quantum computers to simulate quantum systems, right? So chemistry, solid-state physics. And also another aspect that is often forgotten is quantum sensing and metrology, right? So how to use quantum systems to measure, objects or things that we're interested in with the highest achievable precision, okay? So this has given rise to technologies such as measurement of time with the highest possible precision with quantum clocks. It has improved nuclear magnetic resonance devices by generating sensors that have the size, that have nanometric size, for instance, nanodiamonds. Christophe Couteau works also on the topic of nanodiamonds. And also we're developing in Spain, close to Cartagena in Granada, we're developing a quantum mass spectrometer. So single ions that are able to measure the mass of other ions that are sitting next to them, okay, simply by measuring the Coulomb force that one object exerts on the other. So there are many different topics that, span out from the idea of quantum technologies. Today, what I'm going to be talking about is on the topic of how to build a quantum computer, how the idea of a quantum computer in the experimental perspective has been developing historically. You have heard during the lecture series about photonics and probably also about nanodiamonds. What I'm going to be talking about is about the first platform that was proposed for quantum computation. It was proposed by this gentleman here, Juan Ignacio Cirac. He's from Spain, and he's working now in close to Munich in Max Planck Institute for Quantum Optics. He's the director of the theory division there. And also by Peter Zola, who's a professor in Innsbruck, right? So they proposed for the first time in 1995 how to use trapped ions to make quantum computation. So in essence, it was the first ever proposal of how to implement or how to build a quantum computer, right? So we will have a look at this technology, trapped ions, what it means, how to implement this, how to build this, right? But of course, you know that Google and IBM are using another technology, right? They're using these nice, electronic devices, and these are essentially superconducting circuits. So these are the two main technologies, trapped ions and superconducting circuits, that are the main players nowadays in quantum computation, and that we will have a look at how it works and the details of the physics behind, right? So this is the structure of the lecture today. We will have two blocks, trapped ions and superconducting circuits. For the first block, first, we will need to learn how you create ions, how you trap them, how you localize them in a very specific space. Then we will learn about a process that is necessary in the context of trapped ions, which is laser cooling. You have to really stop the ion in a specific space, and you do this with lasers. And then how do you implement quantum gates, and in particular, what was the first proposal of Juan Ignacio Cirac back in 1995 of how to perform a quantum gate. And as you know, if you're able to perform single quantum gates and a C-naught gate, then you have, in principle, the possibility to build a universal quantum computer. Okay? So this will be the first part. For the second part, we'll talk about superconductivity, of course. We will revise what it means. We will talk about Josephson junctions. So what is specifically interesting about Josephson junctions that make them useful for quantum computation. We'll talk about which are the types that are available. And finally, I will talk about Andreev spin qubits, which is a different way to build superconducting qubits, right, that I'm working on directly, and that is hopefully going to become the next technology in this arena. Okay? So if you have any questions or there is anything that is, either too easy or too difficult, let me know, okay? And I'll be happy to answer your questions. Okay, so first part, creating ions. Here we have an atom, a manganese atom, right? You have the nucleus and many electrons around. And the idea is that, very simply, with a laser pulse, you're able to kick out one of these electrons. And instead of having two in the outer shell, you see here the other one, you have just one, right? So this is a positive ion, right? Because it has one electron too little. And with this now, we can do interesting stuff. We're interested mostly on ions on this column here of atoms or elements from this column. Why? Because they have just 2 electrons in the outer shell. If you get one out, you're left with just 1 electron. And then the electronic structure is well understood because, in essence, it's similar to the electronic structure of hydrogen, right? So we like to work with this column here because it's easier to control. Now, okay, this is precisely what I mentioned right now. And they're also very available, right? They're easy to, for instance, calcium. Calcium is very easy to obtain, right? Okay, so calcium is often the type of ions that are used. So how do you trap ions? Well, first, imagine a vacuum chamber, right? So you have nothing, but you have a piece of calcium there, and it has a resistance, an electric resistance. So you let electricity go through, it heats up. This is a very small piece that heats up, and because it's in vacuum, it will evaporate, right? So you will have calcium ions flying into the vacuum, right? And you will have these ionizing lasers like a barrier, right? And whenever one of these calcium atoms, neutral atoms, meets these lasers, then it can be ionized, right? And you can arrange these lasers in such a way that, okay. So as I was saying, by choosing the specific frequencies of the lasers, you can ionize specific isotopes, right? So that you're also selecting whether you're working with calcium-40 or calcium-48, right? And it's important because you need to know the mass of the ion very carefully, right? Okay, so now we have one ion, and what we do is we generate a trapping electromagnetic field, and we bring the ion to a specific position of interest, right? So we've learned about the first step, creating ions. Now we're going to look at trapping ions, right? Because I just showed, okay, you generate an electromagnetic potential, you trap the ion in a specific position. But it's more complicated than it sounds, right? So if you want to trap a charged particle with electrodes, you're going to have a hard time. Why? Well, electrostatics is not enough of a tool to trap ions. So, but let's try. Let's attempt to generate an electrostatic potential, phi, that is good to trap a charged particle. Of course, from phi, if you calculate the minus gradient of phi, you get the electric field, right? And in order to understand how electric fields work, we need to look at Maxwell's laws, right? And the first of these 4 laws, Gauss Law, tells us that the divergence of the electric field equals the density of charge, right? Divided by epsilon 0, which means that if you're in vacuum, as we are, because we have a vacuum chamber and we don't have particles there, the electric field, the divergence of the electric field is going to be 0. It's going to vanish, right? So this is expressed in terms of the Poisson equation here. If we take the electric field and express it in terms of the electric potential, we put it in here and we take this to 0 because we have no charge, then we get this equation here. And what is this equation telling us? Well, the potential, the Laplacian of the potential is 0, meaning the second derivative with respect to the 3 directions has to equal 0. And the last line here tells you the problem that we have here. The curvature cannot be negative in all 3 dimensions, right? So what do you need to generate an electromagnetic potential that is trapping? Do I have chalk here? Ah, there. Awesome. Thank you. Okay, so if you want essentially a potential that is trapping, for instance, in one direction, let's just look at phi z. What does it look, which way does it have to look like? Well, it has to be phi 0 times z squared, right? Because if it's of this form, you have a parabolic potential in the z direction, and it looks like a harmonic well, right? But if you want to do this for all directions, what happens? Poisson equation does not let you, okay? Because if we now look in the 3 directions of space, it is not possible to have a potential of this sort. Because the second derivative of each of the directions does not add up to 0. Unless you have that, for instance, these 2 elements are negative, right? If you have this other situation where this is, phi x and phi y are negative, then you can manage to fulfill Poisson equation, right? So, for instance, a possible electrostatic potential would be of this form, right? This is a valid electrostatic potential following Poisson equation there, okay? So, but what is the problem? This is trapping, but this is a negative parabola, and this is a negative parabola, so it's not trapping. It has this saddle shape, right? So if we now try to plot both directions, x and z, for instance, what we're going to see is we have trapping in this direction, but it's not trapping on the other direction, and what we have here is a saddle potential. Okay, so conclusion, with electrostatic potentials, you can only generate saddle potentials, right? You trap in one direction, but you don't trap in the other one. So this can be also expressed this way. A minimum of the potential cannot be created, only saddle points, and this is actually a theorem from 1833. Okay, so we need to think of other ways to trap particles, and there are 2 alternatives then. If we cannot do just with electrostatic potentials, we need to add other possibilities. We can use a time-dependent potential or a magnetic potential as well, right? A magnetic field. So we have then a distinction between pole traps, also known as radio frequency traps, and penning traps. Pole traps use time-dependent fields. So in average, you generate a trapping field. Penning traps use additional magnetic fields by means of superconducting magnets in essence and cryogenics to produce dynamic trapping, okay? So these are the 2 directions that we can address, and we will understand better penning traps in the travaux dirigés this afternoon. But now let me just show you how this idea works by means of a video. So let's have a look at this, and you'll understand immediately. So essentially, we have this saddle potential. We have here an analogy by means of the gravitational field, right? But to some extent, it works the same as with electrostatics. And of course, this poor man cannot trap this, cannot equilibrate this ball in the saddle, but then introduces a rotation here, a time-dependent driving of the potential. And then at the beginning, there's a bit of instability, but slowly with time, the ball stabilizes there, right? So this is the idea of pole traps. You have a potential that cannot trap, where you cannot equilibrate or localize a particle. But if you introduce a time-dependent evolution or driving, then you can trap. Of course, it is very important that you choose the frequency of this rotation appropriately, right? And you just saw how, as the frequency reduced, then the ball left. But there is also the problem that if you go too fast, then the little instabilities that appear here are too large then. And then you also lose the ion, okay? So you have to choose the frequency very, very carefully. Okay, so okay. No, okay. Good, so this is the idea. The pole traps usually look like this. You have 2 electrodes here on each side, and then 4 electrodes around, like plates, these blades, right? And essentially what this generates is a saddle potential of this form, like the one that we have here in the blackboard. And then what you have to add is this additional potential here that is essentially these 2 alternatives, either positive potential here, negative potential here, so that you have this saddle going, so you have trapping vertically and it's not trapping horizontally. And the opposite is trapping horizontally and not trapping vertically, right? You alternate between these 2 limits with this line here. You realize that it, depending on the cosine of a frequency nu times t, right? So it's time dependent. This is the idea of pole traps. So they're easy to implement because you only need, you see, these blades and electronics to control this time dependence of the potentials, right? But as we saw on the video, they have what is known as excess micromotion, right? The particle oscillates around the center of the potential and has some perturbations. And this micromotion is something that in these experiments one has to be careful with, and this limits then which frequencies you can use here and which intensities you can use for the potentials, right? So you have to fine-tune these details, but it's possible to do. Okay, and panning traps that we will have a look at in the travaux dirigés. You have a trapping potential and not trapping potential, as we had before, and then instead of a time-dependent potential, what you add is a magnetic field, right? And with this magnetic field, we will see that this can generate trapping motion in all 3 directions of space. So the motion here is cleaner. There is no micromotion because there is no time-dependent, there are no time-dependent fields involved here. But as you can see, the trap looks a lot more complicated, right? It needs a strong magnetic field, often superconducting coils, right? And this requires cryogenics and, you know, a very large, cumbersome equipment. Okay, so but in the end, regardless whether you go for pole traps or for penning traps, what you have is a trapped charged particle, right? So you have calcium ion, for instance, calcium plus, that is trapped in a harmonic potential, that experiences restoring force of this form, right? Minus kx, right? The potential is 1/2 of kx squared. And I don't know if you solved this problem from the quantum mechanics perspective. Do you know about Fock states and harmonic trap? Okay, so if you take Schrödinger equation for this kind of potential and solve it, then you will see that you will get quantum states, eigenstates, that have this form, that are, you have the ground state, Fock state number 1, 2, 3. These are all eigenstates of the Hamiltonian, right? So the quantum states that the particle likes to acquire, okay? And then, in general, the motional state of the particle will be a superposition of these Fock states here, right? But a better description for this is a mixed state. So initially, the ion has a high temperature, and it has different probabilities of being in these states, but it doesn't have quantum superposition. It doesn't show quantum superposition. You have the probability to be in 0, 1, 2, but this doesn't mean that you have a superposition that you need for computations, right? So it has a high temperature, in essence. This means it has a high temperature, and we have to cool it down, right? It comes from an oven. You have heated it up. It has been flying through the vacuum chamber, and you need to prepare the ion to cool it down so that it's not, you know, jittering around in the trap, but it's really localized in the minimum. So for this, we are going to do laser cooling. Okay? Laser cooling is a technique that was developed during the 80s, 90s to stop particles, right? You use light to stop their motion. And for this, we need to understand that light can push, right? And this is important because, well, one wouldn't think so by looking at light or even sunlight. It doesn't feel that it can push much, but, well, we have this typical device that shows that indeed light carries momentum. It can push objects, right? And therefore, we have to describe photons in terms not only of their frequency and their associated energy, but also in terms of the wave number and the associated momentum, right? The momentum, the push that a photon has is described by h bar times k, where k is the wave number vector. Okay, so let's imagine a calcium ion that has velocity v, and it finds a photon that has momentum or wave number k, right? If they collide face to face, then after the absorption of the photon by the calcium ion, the velocity will be different, right? It will be v plus h bar k, the momentum, divided by its mass, okay? And notice that this is a vector sum. So because v and k have opposite directions, then the final velocity is smaller. The celerity, if you want, the speed, the momentum, let's say, sorry, the absolute value of the velocity is smaller now because they are opposing. So we have decelerated this calcium ion, right? Now, it has absorbed a photon, therefore the calcium ion is in an excited state. It will emit this photon, right, in some random direction. So the final situation is that, well, you have a velocity that is modified by this vector here. And in the end, well, it has reduced its velocity because it has collided with the photon head-on, but then it has emitted in another direction, so it has some random direction, okay? But this principle can be used, indeed, to stop ions. So let's see how we can do it, and for this we have to make use of the Doppler effect, right? The Doppler effect tells us that if the calcium has a transition of a specific frequency, in this case omega, it will, let's say, absorb a photon only if the frequency of this photon, omega L, coincides with the frequency of the transition, right? Omega L, let's assume it's the frequency of the transition minus some detuning delta, right? It's not exactly the transition, so this light looks red, as we usually say, for the ion. It's too red. It's not resonant. Red detuned laser. But now, if the calcium ion has some velocity and it's going towards the laser, then because of Doppler effect, this laser light, this laser frequency will look larger. It would look of this form, Vk, okay? Now we have a larger frequency, and now this larger frequency can match the transition, okay? So now there is resonance if the chosen detuning is such that the velocity of the calcium ion and its wave number coincide, okay? So it's the same as when you're on the street and you hear an ambulance coming to you. You hear that the noise or the sound is high-pitched. It has higher frequency. And when it goes away from you, it has lower frequency, right? It's lower pitched. So this is the Doppler effect, and this is how we can use this for trapping, because now, if we arrange laser beams in all directions, then you see that the calcium ion is only going to absorb whenever it's moving towards one of the ions in any of the directions, towards one of the lasers in any of the directions here, right? So whenever it tries to move away from its position, then it's going to absorb, and then it's going to be decelerated, right, because of the push of the photon. So this is the idea of Doppler laser cooling. So with this, we can reach temperatures that are around 20 millikelvin for calcium and for traps of 1 megahertz. So this is the limit, essentially. And this limit that I mentioned has to do with the transition that we're using. We're using an electronic transition that has a width of gamma, right, here. And this is the spontaneous emission rate as well. So depending how long it takes for the ion to emit the photon spontaneously that it has acquired, then it will reach a lower or a higher temperature. But this is the first step, Doppler laser cooling, right? So we have now managed to stop the ion in a specific position. But we want to go to even lower temperatures. This is not enough. This is not the ground state. This is not still a situation where you can do quantum operations, right? Because these temperatures are too large, and if you remember this trap and these levels, you're still occupying too many levels. This is about 20 Fock levels. You want to go to the ground state, right? So there are more steps that we need to go for. And for this, we need to understand the concept of Rabi oscillation. Have you seen this before, Rabi oscillation, during the course? No? Okay, so then it's good that I have this, this slide here. So essentially, we have our trap, we have our internal states, our the ground and excited electronic states, and we want to operate with them. For this, we illuminate our ion with laser light, right? And the effect it has in a Hamiltonian is of this form. So this describes this transition here from ground to excited state. This is the Pauli matrix describing this transition. And this Pauli matrix tells us how the laser is going to operate in this transition between ground and excited state. In order to understand the operation, we need to perform a rotating wave approximation. Okay? So this will be part of our travaux dirigés this afternoon as well. We will try to understand where this expression comes from and how we do this step, telling us from here we can actually understand the effect of a laser on an electronic transition in this way. It's just a Pauli matrix and a coefficient which has a frequency here, omega, capital omega, which is the Rabi frequency. Okay? So because for this Hamiltonian, the ground state is actually a superposition of two eigenstates of the Hamiltonian, we will have, in particular these two states, we will have interference effects, right? And probably you have heard about interference effects or interference patterns on the double slit experiment, right? Where you have two ways that light or electrons can go, and then they paint an interference pattern in space, right? Well, because we have generated with this laser a superposition between two states, these two states evolve independently and they interfere with each other. So what you have is this situation where the ground state disappears and appears, disappears and appears with time. These are known as Rabi oscillations, right? So if you're looking for the electron in this ground state, you will see that it's in the ground state, but after a while it's not, and then it's back and it's not. And what happens is that the electron travels to the excited state. So at the beginning it's not in the excited state, but then it is, and it's not, and it is, right? So that the electron is either in the ground state or in the excited state. These are Rabi oscillations, right? And this is what we're going to use in order to perform quantum gates, right? The X gate, the Hadamard gate, and so on. This is the tool that one uses in trapped ions for this. But this is a tool that is also going to be useful to cool the ion down to the ground state, right? We learned about Doppler cooling. We learned that we were populating about 20 of these Fock states, and we need to go down to the ground state. How do we do this? Well, we have our states, right, the trap states. It's important not to confuse the electronic states, so the position where the electron on the ion is, and the motional states, which is how the full ion is moving, right? Okay, but we have these 2 degrees of freedom, and we have a combination of these 2 degrees of freedom. Let me see if I can show you this. Okay, this is what I wanted to show you. The combination of these 2 degrees of freedom gives us this ladder, right? So we have the ground and the excited. And for both the ground and the excited, we have these Fock states here, right? So I arrange these states in this form now. This is just a rearrangement, right? So I have copies, let's say, of the ground and the excited state for each Fock level, right? Good. So what we're going to do in order to go to the ground state is we're going to implement sideband cooling. And for this, we're going to combine spontaneous emission, right? So if the ion is in the excited state, it spontaneously goes down to the ground state. And I'm going to do Rabi oscillations that are going to be of the red sideband type. And this was in the previous slide that I showed you. It is possible with laser light to modify not only to generate absorption to the excited state, but also to reduce the Fock number, right? So what we're doing here is red sideband excitations. Let's go back to the lines that I jumped. So what we have is this Hamiltonian, right? We have the two levels, we have the Fock levels here, and we have the laser light, the effect of the laser light. If we take into account the effect in terms of the position, what we're going to see is that we, again, with a rotating wave approximation, we obtain this other Hamiltonian, right? And if we do things resonantly, we are going to be able to perform this Hamiltonian here, okay? And we're interested in this Hamiltonian because it contains the transitions that we want to implement, right? So I don't know if you're familiar with the creation and annihilation operators, A and A dagger. Have you seen them before in the course? No? A dagger? Okay, so we can generate these operators with trapped ions as well, right? With lasers, you can generate these operators, and it's precisely these operators in combination with the sigma y, you do both things at the same time, so you generate this transition here. Okay? So you combine spontaneous emission, red sideband. And what happens? You go down the ladder, right? So you're forcing the ion to go to the ground state. This is known as sideband cooling. But there are other transitions hidden in this Hamiltonian, right, that are a bit annoying. The carrier excitation, which is going from the ground to the excited state without changing the Fock number. And the blue sideband excitation, which is going to the excited state by adding a Fock number, right? So there's a lot of technology involved in getting rid of these perturbations that make laser cooling less efficient, right? So this is one of the aspects that people work on, and me particularly in the experiment that we're doing in Granada. And the idea is that you get cooling rates that are large enough, and that you get at the same time final phonon numbers and that are small. And you have to be careful with these relationships here with the laser intensity and so on, because it can be, well, a difficult engineering problem, right? So we saw how to create ions. We saw how to trap them with special electromagnetic potentials. We saw how can we use laser cooling to stop them and have them sitting in one specific point of space. Finally, we need to understand how you generate quantum gates with trapped ions, right? So essentially, as you know, you have to worry about generating two types of gates: single ions or single qubit gates and two qubit gates, right? So single qubit gates, we already saw with these Rabi oscillations, you can generate X gates, phase gates, Hadamard gates, right? That's possible simply by shining laser to your trapped ion. The problem is rather two qubit gates, right? So, and for this, it's these two people, Dirac and Zoller, that in 1995 they've proposed for the first time how to implement a C0 gate on a trapped ion. And this was the birth of quantum computation, right? So let's try to at least understand some details about the Dirac-Zoller gate, which is a C0 gate, right? So what you do is you need to have two ions in the same trap, right? And if you have two ions in the same trap, it's useful if they're the same ion, but they can be different ions as well. But essentially, you have ion A and ion B. And you're going to operate with their electronic states, right? The ground state of A, the ground state of B and the excited states of both. And as you know, they're in the same trap. So they share one motional degree of freedom, which is what I paint here with this spring, right? They're two charged particles, so they repel each other because of Coulomb, but they're pushed together because of the trap, right? So we have these two opposing things. In the end, what you have is two ions sitting on the same trap. So in order to perform this gate, what we're going to do is, on these two ions, we're going to combine pulses, and we're going to consider not only the excited and ground states, but also an auxiliary level in one of the two ions. Let me show step by step. So first, the idea is to perform a pi pulse, a red sideband on A, right? So if you remember, let me just paint it here. We have the ground, so the excited and the ground states, right, electronics. But we also have the Fock states, the trap states, right? So this is 0, and this is 1. What is a red sideband? Well, a red sideband is if you have the ion here, you move it to this state. And in particular, pi pulse means moving fully from here to here, not making a superposition, which would be a pi half pulse, but a pi pulse, meaning you go from here to here, okay? So this is what a red sideband means on ion A. When you do a red sideband, you add a phase, right? So this transition here, essentially what happens is, well, essentially what appears here, right? If you start in ground 1, as we had here, you go to excited 0, but you add this minus I here. This is very important. And if you are here, right, and you do this pulse, then you end up here with a minus I as well, right? This is what a pi pulse means. This is essentially a single qubit gate on this transition. The next step is to perform a 2 pi red sideband on B, but using an auxiliary transition, right? So what does it mean? It means that you have another level that we're going to call A, and you perform a 2 pi pulse. So essentially, if we have now these three levels, right? You perform this transition here. So you go from here to here and back, right? That's why it's a 2 pi, full oscillation. And what happens here, if you do a full oscillation, these are qubits. So you need to do this transition twice in order to go back to the initial state. If you do just one of these oscillations, you get a minus sign to your state, right? And this is crucial for our gate. And finally, you do a pi red sideband again, right, on A. So here we have a simplified level structure. Let's look at the actual level structure that we have in this system, right? So we have that the two ions, the first ion can be in the ground and the second in the ground, first in the excited and second in the ground, both in the excited, and the other option, right? So you have all these possible states, and also you have these Fock levels, right? 0, 1. So here we have a qubit from A, a qubit from B, and a qubit from the oscillation, right? So 2 to the 3, it's 8 levels, right? So let's look at what happens in these 8 levels when we perform these 3 pulses that I mentioned. So let's imagine the 4 possible initial states, right? So the ion is in the ground state. We have cooled it down to the ground state. But the electronic can be either here or here or here or here. And the number inside has to do with the phase that each state has, right? So we have these 4 possibilities. If we perform the first pulse, what happens? Well, there are these states that, because they're in the excited and in the 0 state, then they're going to move here. Exactly what I showed here, right? So there are 2 possibilities. When the B is in the excited and when the B is in the ground. We're operating only with the ion A. So we perform this transformation and we gain a phase I, minus I here, right? And the other states are not affected because, well, this state is not affected by the red sideband. Next step is a red sideband on B, right? But notice how, of all these 4 possibilities that we have here, only this one can perform a red sideband, right? Also this one, but we have no population here because we have already transformed everything. And we do this oscillation of going up and down, right? Notice how this is not affected simply because it's in the excited 1, right? So it's in here, and we're only connecting ground state to the auxiliary state, right? So only this one is affected here, and because it makes a rotation, it gives a minus phase. So from minus I, it goes to I, okay? And finally, we do a pi red sideband on A, so we go back to where we came from, right? And in the way back, we get a minus I again. So minus I times I is 1 here. So this will become a 1. And minus I times minus I will become a minus 1, right? So what has happened? Overall, what we see is that we have these 4 possible initial states, and we end up with these 4 final states. And the only transformation that we have done is adding a minus phase here. All the rest remains exactly the same, right? So this is not a C0 gate. This is a phase gate, right? But if you add Hadamard gates on both sides, at the beginning and at the end, on qubit B, then you are performing a C0 gate, right? A control NOT gate. We will understand the details in the travaux dirigés later, okay? So this that we explained in 5 minutes was a revolution in 1995, because it was the first time that somebody explained how these abstract ideas of quantum computation that you have been seeing through the course could be actually implemented in a lab, right? And could be built with specific laser pulses and specific experimental settings. So nowadays, well, you can have really many ions in traps, and you can operate with each ion independently. And there's really many interesting things that have been developed over the years, and they have been good for Nobel Prizes as well. So there's really a lot of interesting stuff going on scientifically in this field. I didn't tell you about how you extract information from the ions, right? You can operate, you can do C0 gates, you can do single qubit gates, but then you have to get information out of it. But it is possible. Essentially, by means of laser, you can read with auxiliary levels whether your ion is here or is somewhere else, right? So this is what is known as electron shelving, right? And this is a process that is possible. So trapped ions, even if people don't hear much about trapped ions, they're actually the platform that offer the best, most accurate control to date, right? And this is an example. And recently, there was this observation of entangled states of 20-qubit system. And people in IBM and Google and so on, they have computers, quantum computers that have hundreds of qubits. But these hundreds of qubits have a lot of noise of the coherence, and they're actually worth very little. There's very little that you can do, very few operations. Whereas with trapped ions, you really get to control a very large amount of them. So there are even companies working in the development, IonQ, for instance. And essentially, the main problem that they're facing, and they're working on this, is scaling, right? You need to, I mean, here we talked about Paul traps and Penning traps, and they all looked really nice. But if you want to host many ions, you have to think of how you design the electrodes in order to make sure that you can isolate ions and you can address them independently, but at the same time, they talk to each other through their motional degrees of freedom. So this complicates their task, but they're making really good progress. Okay, so this was what I had to say about trapped ions, and now we're going to move to superconducting. Okay, so now we're going to continue with superconducting circuits, which is a technology that is maybe more famous nowadays because it's the technology that Google, IBM are implementing in their laboratories, and they're making progress, definitely. So it's a technology that it's worth knowing, at least having an idea of how it's built, what are the components, and how it works, right? So first step is, now it's not working, great. Let's see. Okay, so first is, let's remind ourselves what superconductivity is, right? And in which context can we build a qubit with superconducting circuits, right? So, of course, we all know what resistance is, right? You have electrons flowing through a metal, and these electrons have the ions of the metal on their way, so they have collisions with the ions all the time, and these collisions generate heat, right? So a lot of the energy that is invested in generating a current is lost in colliding with the ions, right? Which is a better picture that we can imagine, right? We have all these ions trying to go through this mesh. We have all the electrons trying to go through this mesh of ions, right? That is on the way. So the thing is, in the end, even if these are collisions, there is a possibility to turn these collisions into quantum interactions, right? These elements that are coming close to each other and that are interacting through their Hamiltonians, through Coulomb interaction in this case. So in principle, there should be a possibility to turn this interaction coherent. And this is precisely what happens with superconductors, right? So the idea is that you generate coherent interaction between the electron and the ions, and then this coherent interaction turns into an attractive force between separate electrons, right? And this is very important because this attractive force then makes the electrons prefer to pair up in Cooper pairs and build a different, let's say, electronic fluid. It's a Cooper pair fluid instead of an electronic Fermi fluid, right? So this association is only thanks to this turning the interaction coherent. But let's try to understand how this attractive force builds up, right? So if you have an electron traveling through this mesh, what happens is that as it goes through, the ions will feel attracted to the negative charge of the electron, right? So they will try to go and, meet this electron that has just passed. What happens then is that you have a higher positive electric charge density here. So the density has increased. And this larger electric charge density attracts other electrons that are around, right? So if you have another electron that is here, it will prefer to go here because there's more electric charge than staying here. Therefore, in average, what we have is that electrons will end up effectively attracting other electrons, but only because there is this mediated activity action of the ion in the background, right? And this is only going to happen when there is a lot of order in this lattice, right? And when is there a lot of order? We're in low temperatures, right? You need very low temperatures so that the ions are very quiet and they are only moving when electrons go past. And then when this is the most important perturbation for the ions, then it is when you have superconductivity. This is a very phenomenologic picture. There is a lot behind, and BCS theory is also only valid for low temperature superconductivity. We have high temperature superconductivity and a huge body of evidence that BCS is not enough, and electron-electron interactions are also important in solid-state physics. But for the moment, it's enough to have just this, to freshen up this idea and to remember that in superconductors, what you have is not single electrons, but Cooper pairs, right? And you have a quantum fluid, let's say, of Cooper pairs going through your conductor. And with this quantum fluid, we can do very cool stuff, and one of them is Josephson junctions, okay? Josephson junctions are just, well, you have to imagine a superconducting lead, right? And you have a barrier at some point in this lead. And this barrier, in principle, is not superconductor, it's an isolating barrier or something that doesn't let electrons through. But there is something happening in quantum physics, which is quantum tunneling, right? Even if you have Cooper pair fluid here and Cooper pair fluid here, you will have a possibility to go through this barrier because of quantum tunneling, right? So essentially what you have here is a wave function that, I don't know, has some form. It tunnels through this barrier and it continues as a quantum wave function here. So we can imagine, right, that we have our wave function that is characterized by a specific wave number. It meets the barrier, so there is an exponential decay of the probability of finding the Cooper pairs. And then after this exponential decay, you have still some possibility to find the Cooper pairs on the other side, right? But even if you have the same wave number here and here, the phase has changed, right, due to this quantum tunneling effect. So the wave function that we have on one side of the barrier is characterized by one phase, but on the other side we have another phase, right? And this drop of phase occurring in Josephson junctions is crucial and is what dominates the the transport properties, right? Okay, this is what I just explained in words. and this is the phase that I was talking about. This change in phase between this wave and this other wave, this phi, is going to dominate the dynamics of this quantum transport. And I won't go through the details because it's a bit long, but essentially what you can find out is that if you do the calculations of how Cooper pairs go through this barrier, you will find that they generate a potential, V, and they generate a current, I. And both the potential and the carrier and the current are determined precisely by this difference of phase between one side and the other. Okay? So this phase difference is crucial, and it tells us everything about the dynamics of this Josephson junction. Now, first important aspect is that normally, if you would have normal conductors and you have a barrier, what happens here is simply that you have a resistance, right? And you would have what? Ohm's law, right? So you will have V equals IR. Clearly, you don't have this law here. V is not proportional to I, right? It's proportional to something else that makes things a lot more complicated. And actually, this looks more like an inductance than like a resistance, right? But it's also not directly, not exactly an inductance. It's something slightly different. So because of this strange relationship between phase, voltage, and intensity, interesting phenomena occur. First, you may get DC current, so continuous current, without a voltage, right? So because the current is only proportional to the phase difference with this sign value, then you don't need a voltage drop. You need a phase drop. And this phase drop is determined by this junction here. You can get alternating current with fixed voltage, right? If you fix the voltage to a specific value, what happens is that you're increasing the phase linearly, right? And because you're increasing the phase linearly, the current is proportional to the sign of something that increases linearly, right? So you have a specific V, right? So essentially phi is V times dt, and with some prefactors, right? So it's proportional to this. And then I is then IC times sine of these prefactors, sorry, not dt, just t, right? So you have alternating current. You have current going up and down your circuit. And you can use this to measure voltages, right? You can use this effect to measure voltages very accurately. And also, if you generate an alternating phase, then you can generate a voltage, right? So you just have to impose some variation of the phase, and this generates voltage. This is similar to what happens when you're doing with the induction law, with Lenz's law, right? If you generate a change in the magnetic flux, you generate a potential, right? So magnetic flux and phase difference, phase drop are related somehow physically. So this can be used as a magnetometer, and maybe you have heard of SQUIDs, right? Superconducting quantum interference device. Well, this is precisely what can be done with a Josephson junction. Josephson junctions are the base for SQUIDs. Okay, so we're interested always in quantum physics, we're interested in the Hamiltonian, the energy associated to a system, because the energy, the Hamiltonian, tells us what the possible quantum states are, right? So you know that I times V is the power of the electric power, right? So if we multiply I and V and integrate over time, we get the energy, right? So with this, if we substitute V and introduce this form of V, we will get the integral of I times the derivative of the phase integrated through time allows us to understand this as an integral of the phase alone, and then with the form of I that is proportional to the sign of the phase, then we get a very simple form for the variation of energy, which is proportional to the cosine, right? So essentially, the energy that is stored in a Josephson junction is simply minus Ej, the cosine of this phase, right? So the phase tells us the voltage, tells us the intensity, but it also tells us about the energy in this junction. And this is very important because this tells us that we have a nonlinear dependency of the value of the energy with the phase. And nonlinearities are essential to obtain qubits, right? So normally when you have a superconducting circuit, you will have a part of the circuit that is a capacitor, right? And the energy associated with a capacitor has to do with how many particles you have inside. This comes simply from the idea that the energy associated to a capacitor is charge squared divided by the capacity, okay? So when you have a capacitor and a Josephson junction, you have this sort of energy landscapes, right? That has to do with how many charges you have in your circuit and the phase of this junction, okay? So this combination provides us with this complicated Hamiltonian, right? That is, on the one hand, a harmonic Hamiltonian, so the sort of Hamiltonian that we have with the trapped ions, right? This potential that is just a harmonic potential, this is the first part, but the second part is nonlinear. So you have to add somehow, this is not exactly true, but you have to add a potential of this form here. And the combination of these two potentials provides us with what we need for a quantum bit. So this is just a quantum harmonic oscillator, right? So if you have a capacity and an inductance, right, a coil, then you have an oscillator, an electronic oscillator, right? This circuit is just like a cavity. And it can be understood in terms of a harmonic trap. And as I said, harmonic traps have these levels. And the thing is that these levels are all of the same distance, right? They all have the same energy difference with all the other levels. So this is not good for a qubit because you don't have selectivity of which transition you want to use for your qubit, right? If you shine microwave radiation here, and you have your electric circuit in this state, you can push it up here, but then if you want to go back down, you won't be able to because when you send another pulse, it will split. It will go up and down, right? So you don't have a qubit. You have many levels to take into account. If you have a Josephson junction here, instead of a normal inductance, you have this cosine term here. And with this cosine term, what happens is that the Schrödinger equation tells us, okay, your difference in energy between 0 and 1 is not the same as between 1 and 2. And this is a bit what happens also in atoms, right? In atoms, the electron that is in the outer shell, it has transitions that are very different in energy, right? So you have very different transitions, and this allows us to select one specific transition. So this is what defines our qubit, right? The fact that we have a transition with a very specific energy. So this is why I mentioned, okay, we have nonlinearity, we have this cosine dependency with the phase, and therefore, thanks to this, we can address specific transitions. Okay, so this is the main trick to build a qubit with a superconductor, right? And with this, you have many different qubit types. And depending, these types depend essentially on whether the capacitive term is more important or the Josephson junction term is more important, right? You have that when the capacity term is more important, you have Cooper pair boxes, right? So with this capacity term being very large, what you have is you have a very tight harmonic potential here. And this means that within this distance, you can only fit a very small amount of levels, right? So this means large unharmonicity. I didn't mention, I believe, what unharmonicity is, but essentially, unharmonicity is the difference between this frequency and this frequency, right? If you're harmonic, if you have a harmonic oscillator, all transitions are the same. If you're non-harmonic, all transitions are different. So this difference in the frequency is what is called unharmonicity. So you have a large unharmonicity, but because your states are very charge-like, they are the number of Cooper pairs, then you're more affected by charge noise, meaning electric fields are going to affect your qubit. And this is going to be noise that you have to shield your circuit from, right? If you have a very large Josephson junction energy, you have less charge noise because your states are more phase states and less charge states, but the unharmonicity is smaller because you have a very broad harmonic potential, and then in this distance you can fit many, many different states which have very similar values of energy, right? So the unharmonicity, as you see, is orders of magnitude smaller, right? The difference in transitions. So you can address these transitions less accurately. But nevertheless, this is still a very important aspect, and that is why essentially all quantum computers of IBM and Google are based on this technology, transmon technology, right? So very important, very large Josephson energies and very small charge energies. There are other family of superconducting qubits, and these are flux qubits. But they're used on another context. They're used for quantum annealing, quantum computation, and I believe you have not really seen that paradigm of quantum computation in this lecture. It's simply a completely different paradigm. Instead of having gates that you put one after the other, what you do is you have a Hamiltonian that describes your system, and then you modify the coefficients of the Hamiltonian. For instance, here we have this Hamiltonian that tells us what the energy states are. And if you modify these coefficients slowly, you may end up with a Hamiltonian whose ground state codifies the answer to an algorithm, to a question, to a problem, right? This is the idea of quantum annealing, right? And in quantum annealing, the superconducting qubits are different. They're flux qubits instead, okay? So this is, for instance, the D-wave quantum computer. Maybe you have heard of it. They are basing their technology on this other paradigm and qubits. Okay, but for Google, for instance, this is the the chip of Google, they use these transmons. And recently, a few years ago, maybe you've heard on the news, that they were able to show quantum advantage using their chip, essentially. This quantum advantage, what did it show? It showed that by using this chip, they were able to solve a problem faster than by using a classical computer. The issue was that this problem was not a specific problem that solved anything useful, right? So it was just showing quantum advantage. They used this word, but we try to avoid it nowadays. It showed quantum advantage, but for a task that was not useful. But that was a very important step forward. Gate operation is by means of microwave driving. And I will show you a specific circuit later, and I will be able to explain a bit more clearly what I mean by this. This microwave driving allows you to operate Rabi oscillations on your qubit of different shapes, of sigma x, sigma y, so you can generate any single qubit operation there. And you just have to make sure that the in-phase driving and the quadrature driving of your microwave cavity is adjusted appropriately. There is qubit capacitive coupling between neighboring qubits that allow you to generate qubit-qubit interactions, right? Oops. And these qubit-qubit interactions are the 2 qubit gates that you need. For instance, CNOT gates, right? So you can do single qubit interactions in all qubits, 2 qubit interactions between some qubits. For instance, this qubit is coupled. You can do a CNOT gate between this one and this one, but you cannot do a CNOT gate between this one and this one, right? So the architecture, then, when you build your circuits and your qubit landscapes, is very important in order to, well, make sure which sort of tasks you're going to be able to perform, right? But this is another topic, quantum chip architecture. We're not going to be talking about that today, but just bear in mind it's an important aspect as well. And the readout is also by means of this microwave cavity. And essentially, what you have is your Josephson junction, your superconducting qubit, your circuit here, and what you have is a readout microwave cavity, right? That by dispersive coupling between the circuit upstairs and the circuit downstairs, dispersive coupling through flux effects, then you can extract what is the current state of this superconducting circuit. Okay. So I would like to, yes, I have time. I would like to talk finally about Andreev spin qubits, which is another family of qubits that we're working on developing. At the moment, we published last year a science paper showing for the first time qubit operation on this sort of new Andreev spin qubits. So let me show you what this is all about. It was in collaboration with Yale University. And the idea is that instead of having a barrier here that you have to go through, you have instead of Josephson weak link, right? We're not talking about Josephson junctions, but weak links. And what are these? Well, if you look at the circuit, we have that the actual superconducting loop is really very small here. This red thing is just the microwave cavity, right? That the readout and operation line, let's say. And this green element here is a superconducting loop, right? And instead of having a barrier in your superconductor, what you have is, you zoom in, these pictures do not correspond to one another, but because they had different samples, but you get the idea. Essentially, you have a gap here in the superconductor, and this gap is covered just by a very thin nanowire. This nanowire is a semiconducting nanowire, right? And it bridges the gap between the two elements of the superconductor, right? So this is just to have a clear idea. We have the readout, we have the loop, and this weak link. Instead of having a barrier, we have a bridge. And these orange and pink lines are just control gates. So how do Andreev states and Andreev qubits work? Well, the idea is that in semiconductors, you have single electrons. The current is formed by single electrons, right? So you have single electrons traveling. But when they reach the interface between the semiconductor and the superconductor, the only way they can jump into the superconductor is by taking a partner, right? They form, the electron takes another electron from the semiconductor, it forms a Cooper pair, and then it can travel through the superconductor, right? If you have an electron and you take another electron, what you leave behind in the semiconductor is a hole, right? And this hole travels back in the semiconductor, right? If you adjust the phase difference in this gap and the energies correctly, the Cooper pair that has traveled around the circuit ends up here on the other end and recombines with the hole again, right? And the electron travels further. So what we have seen here is two instances of Andreev reflection. What is an Andreev reflection? It is essentially an electron that is reflected back as a hole, right? And a hole, oops, and a hole that is okay, now. So an electron that is reflected as a hole and a hole that is reflected as an electron, right? You have that in this semiconductor, you have electrons traveling in one direction and holes traveling in the other direction. So in a way, you have like a photonic cavity, right? You have fermions that are trapped in this space, and they reflect from the ends of the semiconductor, sometimes as holes, sometimes as electrons, right? So in the end, if you have a cavity, right, you have modes building up, right? If you have a light trapped in a cavity, you will have modes. Or if you have the string of a guitar, you have waves traveling back and forth, and you have modes building up in that guitar string, right? So the same here. The interesting part is that we have matter modes, right? And you have these matter modes building up, and these matter modes are fermions, but it's not clear, or it's a superposition between an electron and a hole, right? So that's quite interesting, and this is the sort of particles that we're interested in. These fermionic particles, which are known Andreev quasi-particles, they are fermions, so they have spin, right? All fermions have spin. And we want to control this spin to operate, to do quantum gates with this. And this is something that was not possible until last year, right? So the reason for this was that the control gates that we had did not allow for direct operation, right? So there was this gate controls allowed you to perform excitations to higher lying modes, but it was not possible to transform one spin state into the other spin state, right? So a way to solve this is through Raman transitions and through stirrup, okay? there is something very exciting about quantum states that happens, which is they try to hide from external perturbation if they have the chance, okay? And the idea is that you can use this property to control the state of the spin without directly transforming one spin into the other. So the idea is that the spin-up state is not going to be affected if you try to excite the spin-down to an excited level, right? The other way, the spin-down state is not going to be affected if you're trying to excite the spin-up to an upper level, right? It's not possible. Now, we say that these are dark states, right? So the spin-down is dark to this driving, and the spin-up is dark to this driving, right? So what happens? If you transform your driving slowly into the other driving, right? So I'm driving in this transition here, but slowly I turn on this transition. What happens is that the qubit is going to try to stay hidden from this driving because it's now hidden, it's not seeing the driving. So as you transform it, the spin is going to be pushed into a state that does not see the driving. And this state is, for instance, this one. Well, there's been a problem with the picture here. Okay. But essentially, if you have this quantum superposition, and you have different phases on both transitions, this quantum superposition is special because it's dark to this combination of drivings, right? So by simply pushing the spin into a state that is not affected by this excitation, we have controlled its state, right? So this is known as stirrup. I haven't written the name. It's stimulated Raman adiabatic passage, right? Stirrup. And this is, well, one of the many interesting phenomena, quantum phenomena, coherent phenomena that can occur in quantum systems, and in this case, one with three-level states, right? So this way, we could turn this quantum state not possible to the birth of a new platform, and you can see the details in this science paper here. Okay? So, well, are there any questions about the things that we have seen so far? Maybe online. I don't know if is there a way to see if anybody has a question. If not, if it's not possible to connect to the people at home, we will anyways have discussions on Thursday. So, okay, now it's not working again. So yeah, I mean, essentially, here I had the opportunity to present some of the work that I do, and I work directly also with trapped ions, also with color centers in nanodiamonds. We're doing experiments in Ulm University. We're working with Yale University in terms of these Andreev spin qubits that I just mentioned, so the next generation, let's say, of superconducting circuits. But there are other topics that we work on back in Cartagena, also in collaboration with MIT and National University of Singapore, for instance, in the description of quantum processes and analysis of quantum processes. So these all are topics that we work with. So please bear in mind if you're looking for a bachelor thesis or a master thesis or even to do research with a PhD. Let us know. Cartagena is a really nice place to live, and we have really nice weather and low rents. So yeah, you're very welcome to visit as well. There are possibilities of doing exchanges. If there are no questions, which I believe is the case, then we're going to meet later today at 2, right? Okay, so thank you very much.